Right. So we've seen norm and we've seen orthogonality. Last time we were talking about basis vectors, and very often for convenience we choose basis vectors which have unit length, so unit vectors, so their norm is 1, and we choose them so that they are orthogonal to each other. So for example, so I'm talking about orthogonality and norm in a basis set. So going back to R3, I can choose the following basis, just I hat, j hat, k hat. And in the column vector notation, I hat is just 1 0 0 because its I component is 0, its I component is 1, j component is 0, k component is 0. J is represented as 0 1 0, k is represented as 0 0 1. Question is, are these orthogonal? Yes, because you can check, you can take dot product, inner product of them, and you can check that they are orthogonal to each other. I'm talking about the usual inner product that I defined before. Are they normalized? Normalized means, is their norm equal to 1? Yes. Maybe I should write that down. Yes. Over here, if I take a vector that is normalized, it means that its norm is 1 unit. So yes, these are orthogonal vectors and they are also normalized. So we refer to this as being an orthonormal basis. Let's take one more basis. Suppose I take, so this was 1, let's take the basis given by I plus j and j plus k. So in column notation, this is going to be 1 0 0, this is going to be 1 1 0, this is going to be 0 1 1. Are they orthogonal? No, they are not, because if you take dot product, like for example dot product of these two, you see you will get 1. So not orthogonal. And they are also not normalized because the first vector has norm 1, but this one and this one don't have norm 1, they have norm 2. So they are also not normalized. Mind you, this doesn't take away from the fact that they are a valid basis. You can use them to represent any vector in R3. So they are a basis. It's just that they are not orthogonal to each other and their norm is not 1. And that's fine. They still do the job. What if I take the set I, 2j and minus k? Let's take minus 3k. So in column notation, this is 1 0 0, this is 0 2 0, and this is 0 0 minus 3. You can check these three are orthogonal to each other, meaning they are perpendicular to each other, but they are not normalized because the lengths of these vectors are respectively 1, 2 and 3. So in general, you can have basis set that are orthogonal or not orthogonal, normalized or not normalized. What have I not taken? I have not given you an example of one that is not orthogonal but normalized. Okay, let's construct an example like that. I want something that is not orthogonal but normalized. Okay, so this is example number 4. So let's start with some basic ones. 1 0 0 0 1 0. The third one, I don't want it to be orthogonal to them, or okay, 1 over root 2 0 1 over root 2. This is a basis. This is not orthogonal because if I take dot product of these two, the dot product is not 0. But they are all normalized. You can check that you take any v in a product and it is equal to 1. I mean, for the first two it's obvious. Let's check inner product for this one. So if I call this v, then v is just 1 over root 2 0 1 over root 2 1 over root 2 0 1 over root 2. So this, when you do matrix multiplication, you'll get half plus 0 plus half, which is 1. So it's normalized, but they are not orthogonal to each other. So this brings us to the question of is there, if I have a vector which is not, whose norm is not 1, is it possible to normalize it? Yes, it is possible. You just have to divide it by an appropriate factor. So for example, question is how to normalize a vector. So if I give you some vector, let us call it 1 0 2, and I say normalize it. So first you find out the length of this vector. So its norm is in a product of v with itself. So bra 102 ket 102, which is 1 plus 0 plus 4, which is 5. I should take square root. So the length of this vector is square root 5. So now if I divide the vector by square root 5, you will find that it has become normalized. So if I define, or rather if I redefine my v to be 1 over root 5 of 102, or this is the same as 1 over root 5, 0 over root 5, which is just 0, and 2 over root 5, then you can check that now mod v is going to be equal to 1. Right? So that is how you normalize any given vector, by multiplying it by an appropriate factor. Over here the appropriate factor was 1 over root 5. In general, given any vector v, if I take v and divide it by mod v, this is normalized because this will have length equal to 1. Let's take one more example. If I give you two 1 minus 1, and I say normalize it. So let that appropriate factor which I want to put be n. So let nv be the normalized vector. Therefore, if I take the inner product of ket nv and bra nv, this should be equal to 1. Therefore, remember, if there is a number on the left side, it comes out as complex conjugate. A number on the right side comes out just as itself. Vv is equal to 1. Therefore, modulus n square Vv is 1. Therefore, the number that I'm looking for is just 1 over this inner product of V with itself. So this is just 1 over 2, 1 minus 1 with 2, 1 minus 1, which turns out to be 4, 5, 6, 1 over 6. So the number that we are looking for is just 1 over square root 6. In other words, the normalized vector is NV, which is 1 over root 6 to 1 minus 1. Okay, so in general, this is how you will normalize any vector. Good. The next question that I want to ask is how to write the inner product in terms of the components of a vector. So for this, suppose I'm in some vector space. So let V and W be vectors in this vector space. And there is some basis set. My basis vectors, I'm just calling them 1, 2, I, J, and so on. Okay, these are my basis vectors. So I can write V and W in terms of these basis vectors. So my V has some components, let's call them Vi with the ith basis vector. So this is like V1 times 1 plus V2 times 2 and so on. And similarly, W also I can write in this fashion. So W also has its own components. If you prefer, I'm going to put the index J for this, summation over J. So I and J both go from 1 to n being the dimension of the space. So now if I want to write the inner product VW, this is given by V is summation I what is a nice way to write this? So I will take this summation over I and over J. Now see, V is sitting on the bra side, so they will get complex conjugated when they come out. W's are sitting on the ket side, so they come out as they are. And I, J inner product. So remember, here I and J are the inner products of the basis vectors. Now if my basis is orthonormal, what does orthonormal mean? So I and J are going to be 0 if I is not equal to J, but if they are equal, then it is going to be 1 because they are normalized. And I'm hoping you have seen this notation somewhere. This is referred to as delta ij. This is the Kronecker delta. When I is equal to j, it is 1. When I is not equal to j, it is 0. So for an orthonormal basis set, this is the inner product of basis vectors I and j is just the Kronecker delta, delta ij. So therefore, VW is summation over I and j, Vi star Wj delta ij. Now see, look at this sum over here. This is the sum over all I and j going from 1 to n. So all combinations along with the Kronecker delta. So this is like saying V1 star W1 delta 11, V1 star, let's write it explicitly. So this is, you take the combination of 1 and 1, you take the combination of 1 and 2, and so on till 1 and n. And then 2 and 1, 2 and 2, 2 and n, and then so on till n and 1, n and 2, all the way till n and n. But you will see that whenever the two indices are not equal, the delta is going to become 0. So delta 1 2 is 0, delta 1 n is 0. In the first row, only this delta 1 1 survives. Similarly, in the second row, only the second delta 2 2 will survive, everything else will become 0. Similarly, in the last row, only the last one will survive, everything else becomes 0. So in the end, what you are left with is just the ones in which the two indices are equal. So Vi star W1, V1 star W1, V2 star W2, Vn star Wn. Right. So basically what I've written, I could have just directly, without doing the explicit calculation, I could have said therefore inner product of V and W is just summation I Vi star Wi. Basically in this equation, the summation with delta ij forces all the j's to become equal to I, and whenever j is not equal to I, you don't get anything, that is 0. So summation over ij with the delta ij just removes the j sum by only taking those values of j which are equal to I. So you get this inner product of V with W equal to Vi star W. So this is the inner product of these two vectors V and W in terms of their components. Vi and Wi. And check, this is exactly what we had in our normal definition of dot product, right? Vxwx plus Vywy plus Vzwz. So this comes out because our basis vectors ijk are orthonormal. Very good. The next thing I would like to talk about is how to find out these components. Right in the beginning, I said one of the uses of dot product is to calculate the components of a vector. So the question is how to find the components. I said that if V is Vx I hat plus Vy j hat plus Vz k hat, and if you want the j component of the vector, all you need to do is take the dot product of the vector with the j hat. exactly same thing is going to happen over here. So suppose once again I'm working with the basis referred to as 1, 2, in general j. So that means I can write my vector v as summation over j of some components vj with the basis vector. So if I take the dot product of this, the inner product of this vector v with basis vector I, so I'll say take inner product on both sides with some other basis vector I. So I v is I with this. The vj's are just numbers on the ket side, so I can pull them out. And once again, if I'm working in an orthonormal basis, then as we saw on the last page, inner product of I and j is just the Kronecker delta, delta ij. Once again, I have the sum over j with delta ij, so it only pulls out the value of j which is equal to I. So this is vi. So therefore, you see, by taking the dot product or the inner product of vector v with the ith basis vector, you got the I component of vi out. Similarly, you can check if you want the components of the bra vector. Then you take the dot product with I on the other side and you will get this to be vi star. So in general, given any ket v in terms of its components, so v1 1 plus v2 2 plus the corresponding bra is given by this. And actually, often for the sake of notational consistency, we put the number on the other side. So generally, we write this as 1 with v1 star and 2 with v2 star. Doesn't mean anything because it's just the multiplication of a scalar with a vector. Okay. Let's look at an example of the space of functions. So we had seen the Fourier series in which we wrote f of x as a naught plus a1 cosine 2 pi x by L plus a2 cosine 4 pi x by L and so on, and similarly b1 sine And we had said that these various cosines and sines are the basis vectors, and the a1, a2, b1, b2, a0, these are all your components. So how do you find the component over here? So if I want to find a2, I have to take the inner product of this f with the basis vector, and the basis vector, the corresponding basis vector over here is cosine 4 pi x by l. Right? So we want to take the inner product of these two, and as I told you before, in this space the way to define the inner product is in terms of the integral. So we take the integral 0 to L. Remember, it was defined like this. So I'm going to take the complex conjugate of this cosine, but it's a real number, so it doesn't matter, times f of x dx. And if you remember from when you discussed Fourier series in your math methods course, this is exactly how you calculate a2. In general, any an you can calculate by taking the inner product of a function with the corresponding cosine or sine basis vector. So this is one more way of seeing, this is one more example of how we are using the inner product to extract out the components of a given vector. Okay. So far we have mostly spoken about orthogonal basis vectors. But what if my basis vectors are not orthogonal? Then what? Turns out there is a way of taking a non-orthogonal set and converting it into an orthogonal set. This is a process called Gram-Schmidt orthogonalization. I'm not sure if we discussed this in math methods, and I don't know if we are really formally going to use this a lot. I'll just discuss it qualitatively. What this does is it takes a non-orthogonal basis set and it converts it into an orthogonal basis set. Intuitively, it's very simple what's happening over here. If I give you two vectors, and let's go back to our intuitive sense of looking at it as something that has magnitude and direction, so as these arrows over here. So if I give you two vectors u1 and u2, and I say starting from this, let me make it bigger. Clearly they are not orthogonal, right? They are not perpendicular to each other. So if I say starting from this, you give me a pair of orthogonal vectors. So it's straightforward. You will say, okay, I'll take my first vector, I will define as, so basically u1 and u2 are not orthogonal. So I'll say, I'll take my v1 to be the same as u1. This only. And then I'll say u2, I can resolve it into two components. I can say that there is a component of u2, let's resolve it out. There is one component along v1 and there must be some other component which is orthogonal to u1. So if I subtract out this part, the part that is the part of the vector u2 which is along v1, and I throw it away, then I'll just be left with this. So that I will call v2. So v2 is basically just u2 from which you have subtracted out the component of u2 in the direction of v1. So now you will see V1 and V2 are orthogonal to each other. So I started from U1, U2 which were not orthogonal, and I constructed two vectors V1 and V2 which are orthogonal to each other. I could have started off with three vectors in three-dimensional space. So if there was also a U3 and they were not orthogonal to each other, then again I would define V1 like this. I would define V2 by throwing away the component of U2 which was along V1, and then to define V3 I would have taken my third vector U3 and I would have subtracted from it the component along V1, and also I would have subtracted out from it the component along V2. What I would have left is a component which is both orthogonal to V1 and orthogonal to V2. So then I would have said V1, V2, V3 are orthogonal to each other. So this is the Gram-Schmidt orthogonalization process.